So continuing along, so there's two main types of lasers, CW and pulsed. So CW, that stands for continuous wave. And in a continuous wave laser, the cavities can be operated continuously. So this is a good example of the Heaney laser. That red laser pointer, as you know, you hold the button down and it just operates continuously. Okay? And that has to do with the amount of energy required in the pump and the type of light that we get out. Okay? So that Heaney laser operates without overheating, and so that means it can just continually give laser action. Pulsed lasers, however, are used for certain materials that can overheat as a result of having a population inversion. Remember, that population inversion is in violation of normal, like, thermal room temperature, right? So some materials can get really, really hot when you create a population inversion like that. So hot that it can actually start melting the electronics in here. So typically with those types of lasers, you have to do a pulsed laser, okay? So in other words, what you do is you allow light to build up. You allow that population inversion to build up, and you release this switch that allows all of that built up light that's resonating. So you can see with the switch, it makes it non-resonant. So that switch is going to be somewhere that it won't allow those wavelengths to amplify. Okay, but as soon as that switch is turned off, you can see the distance changes as indicated by the figure, and that gives you this very rapid and instant pulse of light emanating out of the laser. Okay. So typically in a system like this, you'll have, this is what we call the laser train, or sometimes it's called the pulse train. Okay. Because if you're operating your switch at a regular frequency, which you would be, okay? So suppose we're operating that at a frequency of 1 nanosecond. So that would be, if the time between peaks, as indicated here, was 1 nanosecond, that would mean that I would be operating this thing at 10 to the 9 hertz, right? That switch would be opening 1 billion times a second to allow a pulse of light to come through once every nanosecond. So that would start creating my pulse train. But also there's going to be a certain amount of time that switch is open. And that amount of time is typically going to be really, really short, okay? And that's also based on how much time it takes for the laser action, right? For the lifetime of that excited state in the laser action, that's going to decay really fast. So you can see, as this figure shows, you might get a pulse every 1 nanosecond, but the pulse width might be 1 picosecond. So that's 10 to the minus 12 seconds, and that's 10 to the minus 9 seconds. Okay? And as it turns out right now, a picosecond width is quite slow. So we are in the era of attoseconds with current laser technology. So that is 10 to the minus 18 seconds. So I think at this point, one of the fastest laser pulses ever created was around 100 attoseconds. So in other words, like if I zoomed way in on this pulse, the fastest one to date is about 100 attoseconds. So that's 10 to the minus 16 seconds. And that has been designated as the fastest man-made event ever. 100 attosecond laser pulse, right, is the fastest human-created event ever, which is really cool, okay? And so people do use a lot of these ultra fast pulsing lasers to probe the lifetime of an excited state, right? So if your laser can fire ultra fast, like attosecond fast, then you could do the kinetics of an excited state decay, right? So you could actually see how much time it takes for a vibration or a rotation or an electronic transition to go from one state to the next, which is insanely cool. And a lot of that work is going on at Berkeley, at the Berkeley lab.